Hardware fuzzing has emerged as a powerful method for testing CPU functionality, with numerous scientific publications reporting a wide range of bugs. But are they really as powerful as they claim? In our latest project, Encarsia, we set out to answer this question by injecting synthetic bugs into CPUs and testing whether fuzzers could detect them. Before diving into fuzzer evaluation, it's worth understanding how fuzzers work so we can better appreciate the various design choices and their impact on performance. In short, fuzzers are automated test benches. A stimulus generator produces randomized programs, which are then executed on the design under test in simulation. To detect bugs, the same programs are run on a golden reference model, typically an instruction set simulator. Any discrepancy between the architectural state of the tested CPU and the golden model indicates a violation of the ISA and therefore a bug. Most fuzzers also incorporate a feedback mechanism that uses information from previous runs to guide the generation of future test inputs. More recent fuzzers build on this basic architecture, improving or replacing its various components. But what they have in common are impressive numbers. They boast a high coverage on multiplexers, registers, and pretty much any other metric you can think of. But it is not just abstract metrics like coverage that convinces fuzzers of work. They found a lot of bugs. 9 bugs, 16 bugs, 37 bugs. Everybody gets a bug. Naturally, creators use these impressive figures to suggest their approach is somehow uniquely effective. It is their fancy new coverage metric that allows them to find bugs. Or their bug detection mechanism. Maybe they generate inputs in that special way. How nice. The problem? These seemingly strong numbers they build their narratives upon are flawed. Coverage has been repeatedly shown to be an unreliable measure of fuzzer effectiveness. Why? Because it does not account for uneven bug distribution. A targeted fuzzer might explore less of the overall CPU state space, but still find more bugs by concentrating on the regions with the highest density. Furthermore, coverage completely ignores the effort required for a bug to reach an architecturally observable location. Just because a fuzzer hits a buggy component does not mean the bug will be detected. Using natural bug discovery can be just as misleading. Consider these bugs reported by a recently published fuzzer. Impressive? Not quite. Most of the bugs were low-hanging fruit that had only gone unnoticed because this particular CPU had never been fuzzed before. Any standard fuzzer could have found them. Without sound evaluation, it's impossible to separate meaningful innovation from empty promises. This is evidenced by the conflicting claims in the field. Coverage is a great example. The fuzz RTL says it's cheap, and it's what allows it to detect bugs hidden in deep corner cases. Cascade, on the other hand, claims coverage is expensive and ineffective. Is there a better way? Yes. By evaluating fuzzers on robust sets of bugs injected into real CPUs using our new tool Encarsia, we can finally provide reliable, reproducible insights into fuzzer effectiveness. But how do we inject realistic bugs? We surveyed over 1,600 pull requests to find out. Remarkably, all observed bugs fall into just 2 categories: signal mix-ups, which involve confusing similarly named signals, and broken conditionals, which result from mishandling corner cases. Injecting these bugs into RTL is challenging as they affect a wide range of high-level constructs. So, we use an intermediate representation of cells interconnected by wires to enable uniform handling. In this representation, we can inject all possible signal mix-ups by simply rerouting wires. Conditionals, represented as multiplexer trees, can be broken by either removing inputs or by manipulating their select wires. As a final step, we formally verify each injected bug to eliminate any ineffective transformations that could skew the evaluation. Unlike traditional formal verification, which aims to prove that a CPU is functionally correct or secure by verifying a set of high-level properties, we focus on a specific known bug, enabling a more guided and efficient verification workflow. First, we confirmed that the injected bug can induce a local change at the transformed signal. We then verify that the local change propagates to an architecturally visible state. This targeted strategy dramatically reduces the state space, allowing verification to scale to large, out-of-order CPUs. We put Encarsia into action by generating ncorpus, an exhaustive set of bugs spanning diverse CPUs. Ncorpus is publicly available and provides a static ground truth for fair, reproducible fuzzer evaluation. With Ncorpus in hand, we can finally answer the central question that motivated Encarsia: which fuzzing techniques are truly effective? Doing so requires selecting fuzzers that isolate individual techniques. First, we compare processor fuzz and the fuzzer it was built on top of, diffuzzRTL. With coverage guidance turned off, the only difference is that processor fuzz checks for bugs at every instruction, while diffuzzRTL waits until the end of program execution. Yet, both detect exactly the same bugs, indicating that finer detection granularity does not yield better results. Next, we reintroduce coverage guidance to measure its impact. The results remain unchanged. Both fuzzers detect the same bugs as they did without coverage, showing coverage guidance does not effectively guide fuzzers, at least not the one used in diffuzzRTL or processor fuzz. Finally, we tested Cascade, which employs a distinct input generation technique. This time, we noted a significant difference in the bugs found, which demonstrates that it is program generation that drives bug discovery. But Encarsia lets us go beyond identifying broad trends. By analyzing which bugs each fuzzer detects or misses, we can quickly extract insights into their program generation and uncover concrete opportunities for improvement. For instance, these bugs missed by diffuzzRTL all follow a clear pattern. They all involve integer division or multiplication. Further investigation revealed that the cause is a misconfiguration. diffuzzRTL inadvertently omits RISC-V extension from its instruction set. As a result, the affected modules are never exercised and bugs invisible. This illustrates a broader issue. All three of the validated fuzzers ignored large parts of the ISA. Turning to Cascade, we noticed another trend. Many overlooked bugs affect modules related to floating point division or calculating the square root. This is caused by aggressive bug filtering. To avoid repeatedly rediscovering the same issue, Cascade suppresses instructions that have previously triggered bugs. But this filtering is too coarse. Blocking an entire instruction prevents new, distinct bugs affecting that instruction from ever being exposed. Other fuzzers have similar blind spots where poorly implemented filtering mechanisms hinder the discovery of additional bugs. Finally, one may question whether simple syntactic transformations can yield bugs complex enough to truly challenge fuzzers. Broken conditional number 3, injected into boom, provides a clear answer. The bug affects the ring buffer that handles write-back from the FPU when there is contention for general-purpose registers from other execution units. At first glance, the change is negligible, but it makes the write pointer advance regardless of the buffer being full. As a result, the pointer can eventually advance to an entry still holding valid data and corrupt it. Triggering this bug poses two distinct challenges. The first is timing multiple FPU instructions such that when the result of a later instruction is written back, the head pointer must be pointing exactly to the register holding the earlier result. Only then does the earlier value get destroyed. The second challenge is sustained contention in the write-back stage. The buffer is only used when the general-purpose registers are occupied by results from other execution units. If there is no contention, the FPU bypasses the buffer and writes the value directly to the registers without corruption. Together, these conditions make the bug extraordinarily difficult to trigger, as evidenced by the fact that none of the three fuzzers detected it. Moreover, broken conditional number 3 is not an isolated case. Ncorpus includes multiple bugs stemming from microarchitectural corner cases and the general trend is that fuzzers consistently struggle to detect them. If you want to learn more about what happens if we let tools run wild, how accurate evaluation ensures transparency, and see further insights into what makes fuzzers tick, please read the accompanying paper and try out the artifacts.